and welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm finding out how Microchip is powering data centers. I'm joined by Kevin Speer. Kevin is the Technology Director of Silicon Carbide in the High Power Solutions business unit at Microchip. Welcome to the podcast, Kevin.
Thanks, Mike. Thanks for having me.
It's great to have you on the podcast. Can you tell me a little bit about your role at Microchip?
Sure, Mike. So as Technology Director in the Silicon Carbide business unit, my team is responsible for developing the silicon carbide power devices and the packaging that's needed by end users to make their products perform better. This could be through higher efficiency, it could be making the power system smaller and lighter, or it could be about bringing down the total system cost or the lifetime cost of ownership.
That's really interesting, but I know one of the things you do is you really look in depth at applications and working out how to solve problems in applications rather than just provide products. And I think today, we're going to talk about smart energy and smart energy in the data center market. So can you just start off by explaining, what people today mean by smart energy?
For sure. So smart energy relates to the use of technology to make our use of power more efficient and more sustainable. For example, if you have a Google Nest thermostat or a smart thermostat in your home that readjusts when you're not there, that's an example of smart energy. The ability to set your EV to charge only when peak electricity prices are not surging, that's another example of smart energy. Another very simple example of smart energy is the replacement of incandescent bulbs with LEDs. That counts too. So in essence, smart energy uses technology to make energy cleaner, cheaper, and more efficient in our everyday lives.
And obviously one area that is drawing a lot of power is the data center sector. And so, we're going to look at how Microchip helps make smart energy a reality in the data centers. I mean, maybe we can start, really at the low level, at the rack. So can you talk a little bit about how Microchip is delivering power to the rack and within the rack of a data center?
Yeah, let's break this into two parts. So how power reaches the data center in the first place, and then what happens once that power is inside the building. So inside the data center, which, by the way, can be as large as multiple football fields, the computing racks consume increasing amounts of power because of the growing demands that comes from artificial intelligence, cloud services, etc. In the early 2000s, each data center rack would use a few kilowatts of power. Soon, this could reach tens of kilowatts. So to handle that large increase in power effectively, silicon carbide replaces the traditional silicon IGBTs, which can cut power losses by 50% or more, and that allows more compute power in the same rack footprint. Silicon carbide products, including those for Microchip, are available for this part of the story today. Now, if we go outside the data center building, we see in the news that billions and billions of dollars, hundreds of billions of dollars, are being invested in new data centers around the globe. And this, of course, creates massive new electricity demands. Traditional power plants like coal-fired power plants, nuclear power generators, these things take years and years to build and certify, commission, get into operation. And I promise you, Mike, companies like Microsoft, Google, Meta, Amazon, they're not going to wait around for that. Instead, they're going to rely on local renewable energy and microgrids, which requires intelligent, bidirectional power flow. And both of those are two things that today's grid lacks. So solid-state transformers, or SSTs, they enable this by efficiently routing the power. And of course, SSTs will require high-voltage silicon carbide, like Microchip's 3.3 kV portfolio. And these are already being used in some SST prototypes. The future of data center power is innovative and exciting.
That's really interesting. You've covered an awful lot in that answer, Kevin. I think what you're saying is that the demands on processing power, particularly around AI is making the racks draw more power, but also you've got more data centers, so more racks out there. That sounds like a huge challenge. You mentioned SSTs. Can you just unpack them a bit and explain what an SST is and how it differs from a conventional transformer?
Yeah, good question. So the term solid state actually it can be a bit misleading, but it comes from solid state physics, which studies materials in solid form, literally, rather than gas or liquid. Solid state became a popular term in like the 1940s and 50s to describe semiconductor-based devices that at that time were replacing vacuum tubes and things like amplifiers. Today, solid state, that term still refers to semiconductor-based technologies like the solid state transformer. But unlike traditional transformers that are made of iron and copper, and particularly with respect to the grid, those transformers are usually put inside of a metal enclosure and they're literally submerged in a bath of oil for cooling. Unlike those traditional transformers, SSTs use semiconductors, hence solid state, and that makes them smarter and more efficient. So they don't just convert voltage like the conventional transformer does. They can also regulate voltage, they can manage reactive power, and they can also connect directly to DC sources and loads, which makes them ideal for modern energy systems.
And that's really interesting. So presumably you've got a challenge because you're delivering a lot of power at high voltage. Does this mean you're having to develop components that actually can deal with higher voltages than maybe you've developed before?
Yes, higher voltages for sure. And what voltage that is really depends on where in the grid the SST is being inserted. So, for example, there are primary and secondary distribution voltages. Okay. So the primary distribution voltages range from about 4 kilovolts up to about 33 kilovolts. SSTs for primary distribution can and have used devices rated as low as 1200 or 1700 volts in prototypes. But higher voltage devices are, of course, desirable because then you can reduce the number of components in the SST, and that makes it cheaper, it makes it smaller, and of course, it makes it more reliable. On the flip side, there's secondary distribution, which tends to be lower voltages. This is done, ranging anywhere from the outlet in your home, 110, 120 volts, up to about 480 volts three phase. And of course, those can use silicon carbide devices that are available today. And then finally, if you get outside the distribution part, you get to transmission, from the point of the old school central generation, you've got to transmit this power down these long transmission lines. In order to do that as effectively as possible, those transmission voltages are up in the hundreds of kilovolts. So the aluminum and steel lines that are used to transmit the power don't have to be so big and heavy, and they would sag and touch the ground. So the transmission side, at some point, silicon carbide may go there, but it will be quite some time. As for primary and secondary distribution, the devices are available on the market today. And in the coming years, we will start going to higher voltage ratings to go into the primary distribution as well.
So it sounds like these SSTs are expanding out in the network, in the grid. I mean, you talked about microgrids as well, and I'm interested, can you explain a little bit about what you mean by a microgrid and why it's necessary to actually create a grid for a data center?
Yeah, so why it's necessary to create one goes back to what we were talking about earlier, Mike. The companies, I said the companies like Google, Amazon, Meta, Microsoft, they're not going to sit around and wait for 5, 7, 12 years for the local utility providers to stand up a new coal-fired power plant or a nuclear generator, right? So instead, they're going to have local generation, probably through a combination of solar, perhaps wind. There will be battery energy storage on site to capture all of the excess, the surplus energy. So that battery energy storage will come into play and provide power, for example, during the night when the sun is not shining on the solar panels. So that's where your power will be coming from, as opposed to the conventional coal-fired power plant that's hundreds of miles away. And then you're connecting that power generation to the data center building, which of course will be the largest load. But that's not all. You can also connect your EV chargers for your employees who've driven to work. You've really got this sort of microgrid that's local to the data center. And those things, I just had solar installed in my house a few months ago. From the time I called the solar installation company to the time I was generating power was less than 2 months. You compare that to a data center wanting to get, power for their needs. They're not going to sit around and wait years. They're going to create their own microgrid.
And I can certainly see, I mean, it's almost a gold rush around AI data centers at the moment. People don't want to be late. So that makes so much sense. I mean, you talk about this microgrid. It sounds quite complicated. It's not like just connecting to the grid and pulling power. It sounds like you're bringing power in, you're storing power, you're generating power, and potentially, presumably, also shipping power back to the grid.
You described it as complicated, and I'm going to flip that on its head, Mike. I'm going to say the way that we do it today is complicated. Think about it. We generate power at some remote, far off location, spinning a turbine at 3,600 RPM with steam. We generate it at, tens of kilovolts in AC form. We have to boost it up to hundreds of kilovolts. We transmit it hundreds of miles. When it gets to its destination, then we've got to decrease the voltage through transformers, multiple stages. We just got to talking about primary and secondary distribution. It's got to go through all those stages. And then once it gets to the building, then we've got to normally take it and convert that AC down to a lower AC that's safe for humans to use. But then a lot of the loads that we're connecting to use DC power, like the batteries in our electric vehicles. So I think the way that we're doing it today is overly complicated, and the entrance of the solid state transformer is going to be like a universal power router. It's going to have the intelligence and the capability to interconnect AC or DC sources and loads. They'll also be able to regulate the grid and ensure resiliency there. So in my view, the SST and the grid modernization is simplifying what we've been doing so far.
I mean, I get that. I get that this transmission across long distances is really complicated. Is there any efficiency benefit in having local generation and effectively a local microgrid?
Big time. So in 2021, the United States generated almost 11,000 terawatt hours of electricity. By the time we transmit it to its final destination, we only had about 3,700 terawatt hours left to use. All of the rest of that is rejected. It's lost just due to transmitting it from the point of generation to the point of use. So there is massive improvements in efficiency by going to localized generation and use.
So that's incredible, the potential savings by having this microgrid by the data center. Is, this same concept of local generation microgrids, is that going to have an impact outside of the data center market?
Yes, I think it will. I think it will be pervasive across everywhere where electricity is used. I'll give you another pretty staggering example. Also in 2021, the United States used about 4,000 terawatt hours of electricity. The International Energy Agency predicts that electric vehicle charging alone by the end of this decade will add 2,000 terawatt hours of demand. So that's basically saying all of the electricity we use in 2021, half of that is going to be added to our demand by the end of the decade just from EV charging. So when you go back to considering that 2/3 of our electricity is just simply lost due to generation, and now we're going to have all of this demand from EV charging, from artificial intelligence, from the electrification of everything. Yes, this transition in energy generation, distribution, and consumption is going to be mandatory.
And that sounds like a huge challenge and an amazing opportunity as well, that, technology can really solve some of the problems that just building more power stations isn't going to fix.
That's right. That's right. I mean, it's one thing to have a whole bunch of power coming from one location, but it's another to make that same generation amount and make it redundant and make it localized. And the impacts those two things are going to have on how much we actually get to use of what we've created, it's going to be a night and day difference.
I mean, that's amazing. Just in the data centers, the opportunity is mind-boggling. I mean, one of the things I've learned in this podcast series is Microchip does an awful lot of different things, and they provide a lot of solutions for the data center beyond just power. I mean, how are you cooperating with the other parts of Microchip to better understand and better service the data center market?
That's an interesting question, Mike, because today's semiconductor providers are being expected more than ever to provide complete turnkey solutions. Because as you said earlier, this is like a race, a race to get market share. So at Microchip, the business units collaborate in a way that's focused first on the client's end needs. Now, I know that sounds a bit cliche, but at some companies, the different business units are tunnel visioned to the strengths of their own products and their own technologies. And that can lead to either an over-designed, overpriced answer to a misunderstood problem, or it can result in a hodgepodge product that looks like it came from two totally different companies. So anytime Microchip has a collaborative opportunity across business units, we have a laser focus on the customer's challenges and wishes, and we consider how to meet those demands, not how to shoehorn in extra bells and whistles just for the sake of saying we can.
So that sounds really positive. I really appreciate this overview of how, we're bringing smart energy to the data center, Kevin. Just before we go, there's something we always like to get from our podcast guests, and that's, what's the best engineering advice you could give to your listeners?
Yeah, so having lived, breathed, and eaten silicon carbide now for 25 years, what I would say, the advice I have is really tailored to silicon carbide. So high voltage semiconductors are just not what they used to be. The benefits that come with silicon carbide, like a 10x higher power density, up to 80% lower losses, much higher switching frequencies, higher operating temperature, these things don't come for free. So my advice would be, you should go into your next project expecting to learn what design differences are needed with silicon carbide to make the most of all its potential. The end results can be jaw-dropping, but you need to prepare yourself to think differently in order to achieve those results.
I love that. That's great advice. So if people are taking that advice, how can they keep up with Microchip, silicon carbide, and data center solutions?
Yeah, so of course, you can please feel free to contact your local Microchip sales office as a starting point, and they'll relay you to the most appropriate silicon carbide power expert. And then, of course, for all of our product portfolios, application notes, reference designs, all of the silicon carbide stuff at Microchip, we do have a landing page that can be found at microchip.com/SIC.
That's awesome. Kevin, thanks so much for explaining what Microchip is in data center power, and thanks for being a guest on the podcast.
You bet. Thanks for having me, Mike.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.